Hello everyone, and welcome back to the Archive Podcast. I am your host Ichino Ani. Today is Monday, April 13, 2026. I have a truly fascinating and deeply technical machine learning paper to share with you all today. The title of today's paper is What Drives Representation Steering? A Mechanistic Case Study on Steering Refusal. You can find this wonderful research at the coinrads://seth.org/abs/26 04.8524 v1. It is quite a long title, but the content inside is just wonderful and incredibly important for our future with artificial intelligence. Let us start by talking about the big problem this paper is trying to solve. When we build massive artificial intelligence models, we want them to be helpful and polite. But we also critically need them to be safe. If a user asks an AI to do something dangerous, harmful, or illegal, we want the AI to immediately refuse. Scientists call this challenge model alignment. To make the AI refuse bad requests, researchers have recently been using a clever trick called steering vectors. You can think of a steering vector as a tiny mathematical compass. We insert this compass into the hidden thoughts of the AI while it is generating words. This compass points the AI away from bad answers and gently pushes it toward safe refusal. This method works incredibly well in practice, and it is very fast. But here is the grand mystery that the researchers faced. Nobody actually knew how it worked inside the artificial brain. We knew that if we put the compass in, the AI behaved better and refused dangerous prompts. However, we completely lacked an interpretable explanation for the internal mechanisms. Specifically, scientists did not know what internal mechanisms the steering vectors were affecting, and how this resulted in different model outputs. It was like driving a car without knowing how the engine works. If the car breaks down, you have no idea how to fix it or why it failed. These researchers wanted to open up the hood of the AI and map out exactly which gears and wires the steering vector was turning. To solve this mystery, the researchers conducted a comprehensive case study on the concept of refusal. They used two popular open-source language models for their experiments. These were the Gemma 2 billion parameter model and the Llama 3.23 billion parameter model. By using these models, they could look deep inside the neural networks. They proposed a brand new framework called multi-token activation patching. Imagine trying to find a broken wire in a giant string of holiday lights by testing them one by one. Activation patching is somewhat similar. The researchers fed the AI dangerous prompts from datasets like Harmbench and harmless prompts from datasets like Alpaca. They then watched the signals travel through the AI brain layer by layer. They looked at different ways of creating these steering compasses. One method is called difference in means, which compares the average brain activity of safe versus dangerous prompts. Other methods use next token prediction or preference optimization. To their absolute surprise, they discovered that all these different training methodologies were using the exact same pathways inside the AI. They found that different steering methodologies leverage functionally interchangeable circuits when applied at the same layer. There was over a 90% overlap in the circuits they used, but the most exciting discovery was about how the steering vector talks to the attention mechanism. The attention mechanism is the part of the AI that decides which words and concepts are important. It has two main components. One part is called the query key circuit. You can think of the query key circuit as the teacher in a classroom looking around to decide which student to call on next. The second part is called the output value circuit. This part represents what the student actually says when they open their mouth to speak. The researchers found that the steering compass almost completely ignores the teacher deciding who to call on. Instead, the steering vector primarily interacts with the attention mechanism for the output value circuit. It goes straight to the student and changes the actual content of what they are going to say. To scientifically prove this, they actually froze all the attention scores in the query key circuit. They effectively stopped the teacher from looking around and changing focus. When they did this, the performance of the steering vector only dropped by about 8.75% across the two model families. This proved that the steering vector does its heavy lifting almost exclusively inside the output value circuit. Furthermore, the researchers used a mathematical decomposition to look closely at these output value circuits. They created something called the steering value vector decomposition. They found that these circuits represent semantically interpretably concepts. They used a technique called Leggett lens to project these vectors back into human words. Even if the original steering vector looked to have pure random numbers, it was impossible to read. Breaking it down into the output value circuit showed that the AI was activating specific words. It was surfacing words like forbidden, illegal, and dangerous. The AI truly understood the concept of refusal on a human level, and the steering vector was directly triggering those human concepts. Because the researchers finally understood which parts of the AI were doing the work, they tried an amazing experiment. They started deleting dimensions from the steering vector to see what would happen. They threw away 10% and 50%, and then eventually up to 99% of the steering compass. Astoundingly, the AI still refused the dangerous prompts perfectly. Leveraging the activation patching results, they showed that steering vectors can be specified by up to 90 to 99% while retaining most of their performance. They also found that the different steering methodologies all agree on a small shared subset of important dimensions. This means the actual essence of refusal is stored in a very tiny, specific part of the AI. Now let us compare this to other technologies in the field. In the past, to make an AI safe, developers would use prompting. They would simply write a long text instruction telling the AI to be good. But bad actors could easily trick the AI into ignoring the prompt using jailbreaks. Another common technology is fine-tuning. Fine-tuning requires changing the actual core memory of the AI by retraining it on thousands of computers for many days. It is incredibly expensive and sometimes makes the AI forget other important facts. Steering vectors are so much better because they are lightweight and act instantly at inference time. But now that we know we can make them 99% smaller, they are more efficient than anyone ever thought possible. Let us talk about how this amazing science can be applied to our everyday lives. I will provide day-specific application examples based on the content of this paper. The first specific application is making smart educational toys completely safe for children. Imagine a robotic language tutor that helps kids practice reading. Parents want to be absolutely certain the robot never discusses adult topics or dangerous activities, because this paper proves that steering vectors can be shrunken down by 99%. Toy companies can easily fit these tiny safety compasses into the smart computer chips inside toys. The tool will actively refuse bad topics using the output value circuit without needing a massive and expensive internet connection to a supercomputer. It brings perfect safety right into the playroom. The second specific application is building highly reliable customer service chatbots for hospitals and clinics. When a patient talks to a hospital AI to schedule a checkup, it is very dangerous if the AI accidentally tries to diagnose an illness or give medical advice. Or using a mechanistic understanding from this paper, developers can precisely insert a steering vector that targets the exact output value circuit responsible for giving advice. The AI will gracefully and politely refuse to act as a doctor, keeping patients safe from incorrect medical information. Because we now know exactly how the circuit handles refusal, the hospital can trust the AI more than ever before, diagnosing failure cases easily. The third specific application is bringing powerful, perfectly aligned AI directly to our everyday smartphones. Right now, running a safer online AI usually requires giant servers in the cloud, because the safety filters are too heavy for a phone battery. But this paper showed that different steering methodologies converge in a tiny shared subspace of important dimensions. By extracting just this shared subset, phone manufacturers can build incredibly lightweight safety filters. Your phone will be able to process personal data, write emails, and answer questions safely while completely offline. This protects your privacy and saves your battery life, all thanks to understanding the hidden mechanisms of the AI. Wonderful to see scientists opening up the black box of artificial intelligence, are mathematically mapping out how these models actually think and refuse. We are moving away from magic and moving toward real science. We can build a future where AI is helpful, completely transparent, and mathematically proven to be safe for everyone. Thank you so much for joining me today. I hope you found this deep dive into the mechanics of machine learning as exciting as I did. Keep wondering, keep learning, and be sure to tune in next time for more amazing discoveries from the archive.